Have you ever stopped to think about how your computer or your phone actually solves those massive, complex equations from your calculus class? I mean, they don't just think about it the way we do. Turns out they use this incredibly powerful, really elegant method to turn what looks like chaos into something orderly. And today, we're going to pull back the curtain and show you exactly how it works. All right, so check this out. Take a look at this differential equation. We've got a third derivative, and it's equal to t. Now, this is the kind of thing that pops up everywhere. Physics, engineering, you name it. But how does a machine even start to tackle this? It looks pretty intimidating, right? Well, that's where this clever trick comes in. So here's our game plan. First up, we'll reveal that clever trick I'm talking about. Then I'm going to give you a universal recipe that you can use every single time. We'll see that recipe in action with a classic example, expand the menu to a few different types of problems, and then wrap up with the ultimate takeaway on why this matters so much. So what is this big secret? Honestly, it's surprisingly simple. Instead of trying to wrestle with one giant, high-order equation, computers use a divide-and-conquer strategy. They break it down into a bunch of smaller, way more manageable first-order equations. It's brilliant, really. And this is the goal. This is what the computer wants to see. It's a system of first-order equations, all neatly packaged in matrix form. You can think of this as the universal language for pretty much any computational solver out there. So our job is to become translators, to turn any high-order equation into this beautiful, organized format. So how do we do that translation? Well, we use a simple, step-by-step recipe. This isn't about guesswork or intuition. It's a totally methodical process. And once you've got it down, you can apply it to almost any differential equation you're ever going to see in your courses. Let's break down this recipe. Step 1, we define a chain of new variables. x1 is just our original function, y. x2 is its derivative, y prime. x3 is the second derivative, and you just keep going. Now, step 2 is the easy part. It's almost a freebie. The derivative of x1 is just x2. The derivative of x2, it's x3. See the pattern? The only place you have to do any real work is step 3, where we use our original equation to figure out the very last derivative in the chain. Okay, theory is great, but let's get our hands dirty and make this concrete. We're going to put our recipe to the test with a classic second-order differential equation. Seriously, this is the kind of problem you will absolutely see on an exam, so let's nail it down. Here it is. Our mission, should we choose to accept it, is to convert y double prime plus 3y prime plus 2y equals 0 into that clean first-order matrix system. So let's get cooking. Okay, step 1, define variables. It's a second-order equation, so we only need two. x1 is y and x2 is y prime. Easy enough. Step 2, find the first derivative. Well, the derivative of x1, which is y prime, is simply x2. Done. Now for step 3, this is the key. We need to find x2 prime, which is the same as y double prime. So we just go back to our original equation and solve for it. And be careful here. This is a super common spot for a mistake. Notice how the positive 3y prime and 2y become negative when they move to the other side? Watch your signs. Finally, step 4, we just swap our new variables back in. And bam! This is the payoff. On the left, we have our two new first-order equations. x1 prime equals x2, and x2 prime equals minus 2x1 minus 3x2. From there, you can literally just read the numbers right into the matrix on the right, row by row. How cool is that? It's clean, it's organized, and it's exactly what a computer needs to get started. So our recipe worked like a charm for that standard example. But what's really great about this method is just how versatile it is. It's not a one-trick pony at all. So let's expand the menu and see how it handles a couple of different situations. Now this is interesting. Sometimes a problem is handed to you already in a near-perfect format. Here we've got a system that describes the salt concentration in two connecting mixing tanks. It's called a coupled system, which is just a fancy way of saying the equations are linked. You can see right there that the change in the second tank, x sub e, depends on what's happening in the first tank, x sub a. And in a case like this, you don't even need the recipe. The hard work is already done. You can just read the coefficients directly from the equations into the matrix. The first equation gives us that top row, and the second equation gives us the bottom row. It's that straightforward. Okay, let's turn the difficulty up a notch. Remember that problem from the very beginning? A third-order equation, and it's non-homogeneous because of that little t hanging out on the right side. So, the big question is, does our recipe still hold up? Let's find out. You know what? We just followed the exact same steps. It's a third-order problem, so now we just need three variables, x1, x2, and x3. The derivatives are just as simple as before.
x1 prime is x2, and x2 prime is x3. And for that final derivative, x3 prime, we just rearrange our original equation to solve for y triple prime. That gives us y plus t, or x1 plus t. See, the recipe scales up perfectly.
And here's the final result, but with a little twist. The main matrix part forms just like before. It shows how all the state variables, x1, x2, and x3, interact with each other. But what about that extra t? Well, because it's an external input, it's just a function of time, it doesn't depend on y or its derivatives, it doesn't fit inside the main matrix. So instead, it gets its own separate input vector that gets added on.
So we've learned the recipe, and we've seen it in action on a few different problems. But let's zoom out. Why did we spend all this time learning this specific conversion technique? What's the big picture idea here?
This is it, right here. This is the fundamental principle. If you remember one thing, make it this. Any differential equation, no matter how crazy high the order is, can be broken down and rewritten this way. It's a universal truth in math, and it is incredibly powerful.
And that power isn't just theoretical. This isn't some abstract exercise you only do in a math class. This conversion is the foundational technique that lets software model weather patterns, design electrical circuits, simulate financial markets, and even analyze vibrations in a bridge. It is literally the engine running under the hood of modern science and engineering.
So now you know the computer's clever trick. You've got the universal recipe. The only question left is, are you ready to put it into practice and try it yourself? Go on. Find a problem and see how this powerful technique can turn something complex into something crystal clear.